will get started. So we're very fortunate. Actually, we're recording now. Yes, good.
Yeah,
okay. So we're very fortunate to have Hani Farid to give the second keynote. Hani is now a professor at Berkeley, and before that was a professor at Dartmouth, right? I think, and he does image forensics and has been doing this for a very long time. He is one of the people who people go to whenever they want to know if an image looks like it's real or fake. And we're very fortunate to have him because one of the main problems that people always point to in adversarial machine learning is, well, what real problems are you trying to solve? Like, you're sort of working in this toy space of making pandas look like gibbons, but like, why does it ever really matter? And Hani comes from a world where it actually matters. And so with that, Hani, please go ahead.
Okay, thank you, Nicholas. I like the introduction of "what I do matters." That's really about the most flattering thing somebody could say. Thank you. So I'm going to talk today about some work that we've been doing for the last year and a half. As Nicholas said, we've been thinking about this problem for over 20 years in the sort of Photoshop age. And as we've come into the machine learning and deep learning and big data, the ability to create and synthesize fake media has, of course, gotten much more sophisticated. And we in my lab here at Berkeley are interested in detecting these types of manipulations. And the work that I'll describe is that of Shruti Agarwal. She is a now fifth-year PhD student, really super terrific. And the three projects that I'll describe, time permitting, are all work that she's been working on as part of her PhD dissertation. So you've probably heard the term deepfake, but just in case you haven't, I'm going to just spend a few minutes just talking about it. And by way of example, let me just start by sharing what is one of my favorite so-called face swap deepfakes. So let's go ahead and watch this video, and then I'll go ahead and explain what you're seeing.
Expected Amy to win, so I just like, it was just, this was very truly surprising for me.
Okay, so what you're seeing on the left is Jennifer Lawrence, of course, accepting an award, and on the right is the result of a face swap deepfake, where of all people, Steve Buscemi's face has been swapped in. And this is, of course, done frame by frame by frame by simply synthesizing what Steve Buscemi should look like and then smoothly generating that in. And you can see it's actually quite effective, and certainly for comedic effect is quite good. The things we worry about are not that kind of comedy. In fact, we welcome that. We welcome the introduction of Nicolas Cage into The Sound of Music. We think it's fantastic. But with that technology, of course, comes things that are less welcome. And probably right now, where you are seeing the majority of the misuse of this type of technology is in the form of non-consensual pornography, where a woman's face, typically a woman, is added into sexually explicit material, and that material makes its way online. That's happening to performers, it's happening to politicians, it's happening to human rights activists, it's happening to reporters, and in some cases happening to people who grab attention, unwanted attention from trolls on the internet. And that's a major problem in terms of technology and policy for us to deal with. Coming off of the 2016 campaign, entering the 2020 campaign here in the US, and certainly if you've been paying attention to the information apocalypse that has surrounded the COVID crisis, we are concerned about how this type of technology will inject itself into existing misinformation campaigns to make them even worse. I come initially in this work from the courts of law. How do you think about authenticating material, whether it's video or image or audio in courts, where the stakes are very, very high, people's lives are literally at stake? How do you authenticate digital evidence? Obviously, there are national security concerns both here and abroad, and of course, the ability to commit large-scale fraud. So just for that last one, imagine, for example, we create a deep fake of Elon Musk saying profits are down 20%. That goes viral. 30 seconds later, the market moves a couple $1 billion before anybody corrects the record. And in each of these instances that I've described of the misuse of this type of material, the concern is not just the material, but how fast it works. That once this stuff is online, it never really comes offline, and the impact that it can have can be very fast, furious, before anybody gets a handle on these things. And that's why we are starting to think about detecting these types of deepfakes. So let me just start with a very simple taxonomy. I showed you a so-called face swap deepfake, where one person's face, typically from the eyebrows to about the chin, is replaced with another person's face. There are 3 categories of deepfakes. The other is a puppet master, where I take a single image of a person, let's say Vladimir Putin, and then I sit in front of a webcam the way I'm doing right now, and as I move my head, as my eyebrows and my expressions, it will animate his entire face in the same way, and then of course you just inject an audio track into that, and you can literally be the puppet master for anybody. And the third type is a so-called lip sync deepfake, where you take an otherwise authentic video and you simply replace the mouth to be consistent with a new audio track. Okay, so notice that in each of these deepfakes, a different component of the face is being manipulated. The mouth, lip sync, the face, eyebrow to chin for face swap, and the entire head for puppet master. But in each case, the commonality here is that it is not the person it purports to be, right? And I mention that because that's how we're going to think about this problem. We're not going to think about it as going after some artifact that is introduced due to the synthesis process of creating a deep fake. Nothing wrong with those techniques, but as Nicholas will tell you, they tend to be very vulnerable to attack because they tend to pick up on these very fine-grained artifacts. We're going to go after something more fundamental, which is it's not Mark Zuckerberg, it's not Vladimir Putin, and it's not Steve Buscemi in the way the person is talking and moving and expressing themselves. Okay, so by way of motivation for how we think about this problem, what I'm showing you in the top here is one frame of an authentic video of President Obama doing a weekly address. And on the bottom is a graph of 2 things over a period of 10 seconds. Okay, so about 240, 300 frames, depending on your frame rate. On the vertical axis is the amount of energy of 2 types of facial movements. One is the rotation of the head around the x-axis, so that's in blue, so how much am I rotating my head up and down? And the orange is the action unit or facial expression of frowning, turning down the sides of your mouth. Okay? And the graphs that I'm showing you are averaged over hours and hours of video of President Obama giving weekly addresses and speeches. And what you can see here is that they're correlated. So when he rotates his head up, he smiles, and when he rotates his head down, he frowns. It's the sort of characteristic that he has. So when he delivers bad news, and once you know this, by the way, if you watch his speeches, you'll see it. When he delivers bad news, he just tilts his head downward a little bit. And when he's sort of cracking a joke or delivering good news, he tends to tilt his head upwards. And it's just a characteristic or a behavior, if you will. Now, when I create a lip sync deepfake of President Obama, so this is one frame of a lip sync deepfake, what have I done? I've decoupled the mouth from the rest of the head. So the head is saying something in the original speech, but the mouth is now saying, well, whatever the impersonator has them say. And so I've decoupled them. I've created a chimera of sorts. And now in the graph, you can see, again, blue is rotation around the x-axis, orange is frowning, that they've been decoupled. They are now desynchronized because of the nature of a lip sync deepfake. And this, in a nutshell, is what we're going to go after. Now, of course, this head rotation and frowning is something that we've uncovered that is specific to President Obama. Not everybody has that characteristic. So, for example, if you look at the current president, and again, on the horizontal axis, let's look on the left, that's authentic, on the right is fake. So on the left in the bottom is time, 10 seconds again. Vertical axis is the energy of now 2 new facial expressions. The chin pucker, if you've ever seen the president do this, he does this thing where he puckers his chin. And then the orange, that's in blue, and then the orange is the mouth open. And here you can see that they are anti-correlated. So when his chin is puckered, his mouth is closed, and vice versa. On the right is Alec Baldwin from Saturday Night Live, who does a fantastic Trump impersonation. And here you can see that when Trump does the impersonation, he has correlated the chin pucker with the mouth open. And this in many ways is the nature of an impersonation, right? You pick up on a very characteristic feature. And for Trump, that's how wide his mouth is and the chin pucker. And you just do it, but you don't necessarily get the temporal dynamics right. And since you don't really notice these things as us as the observer, it all seems to work out. But you can see again, this is, by the way, I meant to mention, is a face swap deepfake, where now the issue is not that I've decoupled the mouth from the head, it's that the person talking is literally not the person that it purports to be. It's only that person from eyebrows to chin. Okay. So for the face swap and the lip sync, I've already explained why we can go after these characteristics. Face swap, the person moving, talking, moving their head is somebody else. In the lip sync, I've decoupled the mouth from the head. And of course, for the puppet master, it's sort of like the face swap. The person who's talking is not the person who purports to be. So for each of these types of deep fakes, going after these behavioral components promises to be able to detect them regardless of the synthesis technique and regardless of the specific type of deep fake. And having been in this business of forensics for a long time, it is very much an arms race. And I don't have to tell people in the security world how hard that is, because every few months there's a new synthesis techniques. But to the extent that they fall into one of these categories, we hopefully will have a mechanism to detect them. And that's what we're going to talk about right now. Okay, so let me talk about the sort of the precursor to the technique that I wanted to talk about, just to give you a way of intuition and motivation for why these behavioral components work. So the first thing we're going to do is we're going to take a video and we're going to carve it up into 10-second clips. And that's just an experimentally determined number. And for each 10-second clip, we're going to do standard face tracking. So the blue box is doing 3D head rotation. The green lasers coming out of the eyes are eye gaze. And then all the blue dots on the faces are simply facial markers that are tracked over time. So this is standard face tracking. OpenFace does it very well, highly stable and reliable now, particularly with politicians, because they tend to be squared in pretty tight, high resolution, looking at the camera, talking, quintessential talking head. So we take the output of that and we decompose that data into so-called action units. And I'm showing you here 12 of 18 action units that we express that capture different facial properties. So the mouth open, the furrowing of the brow, the frowning, and so on and so forth. So there's 18 of action units that the facial expression, the facial features that I tracked in the previous slide get boiled down to. And then we look at two head movements, rotation around X and rotation around Z. And we ignore rotation around Y because when politicians speak to large audiences, they do this a lot. And it turns out it's just not very diagnostic. So we just ditch that head rotation. So we have now at every moment in time, for every frame, 1/24th, 1/30th of a second, we have 20 measurements. How much of a particular action unit and how much is the head rotating. And we simply look, thinking back to what I showed you earlier, at the correlation between all pairs of those 20 measurements. So that's 20 choose 2, that's 190 correlations. And we're going to ask things like, is the chin pucker anti-correlated to the mouth opening? Is the rotation around the x-axis correlated to the frowning, and so on and so forth? And we're going to do that on a per individual basis. So I get 190 measurements for every 10-second clip. And of course, for any individual, I get many of those 10-second clips. And what I'm going to do is I'm going to take that 190 dimensional feature and I'm going to slam it down into a 2-dimensional space so that you can visualize it. And that's what I'm showing you on this slide. Every dot on this slide corresponds to a 10-second clip of an individual whose names you see here. These were, of course, generated during the Democratic primary here in the US. So a couple of things that you notice. So first of all, Clinton, Warren, Sanders, Trump, Booker, Biden, Buttigieg, Harris, Obama, and O'Rourke are all clustered into their own nice little areas. And that means that we have captured something that is distinct to that individual. The light blue that you see here are random people taken from the so-called face forensic database, and they're not one individual, which is why they're scattered about. And then most interestingly is down here, the deep fake Obama in the brown, you can see are separated from Obama. Now, again, we're not really in the business of saying, is this a deep fake Obama or an Obama? What we're interested in is it Obama or not Obama, right? So we simply want to ask, are the dynamics and the behavior consistent with what we see from this particular individual? And to that end, what we're going to do is a very simple, in this first cut, I'll explain a second cut of this in a few minutes, is a simple one class nonlinear support vector machine working in the original 190 dimensional space. And for that, for the training, of course, I don't need any fake data. All I need is lots of authentic videos of Obama. That's easy to get. Same for any of the people that you see here, particularly good for world leaders and candidates and actors and actresses and CEOs. And then we simply ask for any 10-second clip, are you inside or outside of that cluster? So very simple cluster analysis. Okay, so let me show you some detailed results on Obama, and then I'll show you some general results on a few other people, and then we'll get into the next stage of the talk. So we started with a number of different videos, and I'll give you the numbers of those in a second. We have authentic videos of Obama, some lip sync deepfake of Obama, somebody who's just impersonating Obama. So this is a perfectly authentic video, but it's just not Obama. A face swap of Obama where we put Obama's face onto the impersonator, and then some Puppet Master deep fakes. So the lip sync, the face swap, and the Puppet Master are the deep fakes. The Obama is the original, and the impersonator is an original video, but it's not Obama. And so from our purposes, that's not authentic. Okay. All right, so we have a total of 207,000 and change 10-second clips of Obama. Super easy to get. You scrape YouTube, you get a ton of video, right? We have 30,000 random people, primarily newscasters taken from the Face Forensic database. We have 2,000 impersonators or comedic impersonators, and about 17,000 total lip sync deepfakes. Deepfakes of face swap, lip sync, and Puppet. Again, these all correspond to 10-second clips is what I'm talking about. And now what we're going to do is we're going to build a one-class support vector machine for the authentic Obama here. And we're going to ask how well can we discriminate authentic Obama from random people, the comedic impersonators, and the deep fakes. And I'm going to specify the results in terms of AUC. An AUC of 1 means perfect classification. An AUC of 0.5, of course, means chance. Okay, so let's see how we did. So again, this is accuracy on 10-second clips. So you can see discriminating Obama from random people, impersonators, face swap deep fakes. Let me skip this for a second. And then Puppet Masters is around 0.95 or so. So doing pretty well. And here you can see we're really struggling. We're just slightly over 0.8. And in many ways that makes sense, because if you think about the nature of a lip sync deep fake, the entire video is real except for the decoupling of the mouth, right? So in fact, the eyebrows are moving consistently, the head is moving consistently, but it's just the mouth that is wrong. And so that should be harder. That's intuitively, it should be harder as compared to a face swap and a Puppet Master where the entire head and behavior are completely inconsistent with the individual. So that's, in some ways, that's good news and makes sense. Now, if I integrate over the length of a video, which tends to be on average about 3 minutes, by simply doing a majority votes, you can see we get a bump across the boards. So the lip sync deep fake detection goes up to about 0.95, and everybody else goes up to 0.9 and 95 and higher. So we're doing actually fairly well there. Now, it's obviously not just an Obama detector. So let me just show you what our accuracies look like for Hillary Clinton, Bernie Sanders, Donald Trump, and Elizabeth Warren. Again, AUC on the vertical axis, 0.5 is chance, 1.0 is perfect classification. And you can see again that for the most part, we're above a 0.9 accuracy, struggling a little bit on the face swap deep fakes, primarily because Alec Baldwin does a really good Trump impersonation. Okay, now, it should become immediately apparent to you that this must not be an optimal classifier, because the features that we used are handcrafted. We started with this intuition that we can capture behavior, and the way we did that is by looking at these action units, looking at the correlation across 10-second videos, and then trying to build classifiers. And it works fairly well. You're getting AUCs above 0.9, 0.95, but obviously those handcrafted features are gonna have trouble competing with learned features. And so what I want to talk now is with this by way of intuition and understanding that there is a signal here, there is a behavioral signal. How do we sort of optimize that behavioral signal? Okay, and that's what we're going to talk about next. All right. What we're going to do is we're going to try to learn these behavioral features, and I'm going to describe that system for you now. So we're going to start with a FabNet. This is some nice work from Andrew Zisserman and his colleagues from 2018. And what FabNet does is it takes a single image and it pushes through a deep neural network called FabNet. And it boils down to a 256 dimensional feature that captures facial attributes. So for example, if you grab a 256 dimensional feature vector through this FabNet for this query image, and then you ask for the nearest neighbors in that embedding space, you will get these 5 images. And you can see that it's basically sort of getting the pose and the expression right. The mouth is slightly open, the head is slightly tilted, but it has nothing to do with identity, right? It's not interested in identity at all. Same thing here, eyes slightly closed, mouth slightly open. These are the 5 nearest neighbors to the right. Same thing here, head is rotated a little bit, and these are the 5 nearest features. So that's not a bug, that's what it was designed to do. It's capturing facial attributes, but not identity. So we care about both of those things. We care about facial attributes and identity. So we're gonna use this FabNet as a starting point because we know that it captures facial attributes. So you can think about the FabNet as replacing the action units that we handcrafted. And now we're gonna use these learned features as part of a larger pipeline, which I'll describe next. Okay, so we take 100 frames now, so that's about 4 seconds of video at 25 frames a second. And we pack in the 256 dimensional feature vector that comes out of the FabNet, which of course captures the facial attributes at each moment in time. So I now have 100 by 256 dimensional matrix. And we shove that into our new deep neural network called the behavior net. Now, I'm not going to spend a lot of time talking about the architecture and the learning and all that, but let me just give you some bullet points. So the underlying training data is Vox Celeb. This is a nice large data set of celebrities talking. We use a standard ResNet 101 architecture, and we have a very straightforward metric learning objective function where we're trying to essentially cluster people with the same 100 by 256 features into separating clusters so that we learn that what is it that this feature vector 512 should capture both identity, who you are, and behavior, how are you moving your expressions. Okay, and so that's the underlying objective here. So just to give you a sense that that works, here's a query image, a video rather, 100 frames on the left. And what I'm showing you to the right are the 5 nearest neighbors. And now notice, unlike FabNet, first of all, it's the same person. Good, that was by design. We wanted to capture identity. And also notice that the videos are actually highly similar, right? He's moving his head. His head is rotated slightly to the side. And of course, he's talking. And that's what we're capturing here in the 5 nearest neighbors. Similarly, for the next frame, query image on the left here, and these are the 5 nearest neighbors. And again, you can see that he's talking, and then there's this quick rotation to the left, and that's what we're capturing in the nearest neighbors here. And one more here. Query video on the left, nearest neighbors here. And again, you see you're capturing both identity and behavior, which is what we set out to do. Okay, so that's good news now. Okay, so that captures behavior. And now we're also going to do is capture appearance. So we're going to take each image from each frame. We're going to shove it into a standard face recognition classifier. We're just using VGG for that. I don't think there's anything special about that. You could have put anything you want in there. That reduces each frame into 4096 dimensional vector. We take all 100 of those and we simply average them together, literally a straight average, because the identity should be the same across the video because it's the same person. So now, if you will, in green here, I have a 512 feature vector that captures behavior and identity, and based on the dynamics of how you move. And in the orange, I have facial recognition, identity based only on your appearance. And now we're going to ask, are these consistent with a reference set? So in particular, the reference set is, as I showed you earlier, a bunch of authentic, validated video of each individual, Obama, Biden, Harris, Clinton, etc. And what we're going to do is we extract, of course, the same 512 and 4096 dimensional features for them. New video comes in, shove it through FabNet, shove it through VGG, shove it through BehaviorNet. Out comes a new feature vector, and you simply poke into your reference set and you ask, who am I most similar to? So behaviorally, you'll come out with one identity, IB. For face, you'll come out with another identity, IF. And of course, what we want to know is, are those the same identity? So for example, if it's a face swap deepfake of Alec Baldwin moving with Donald Trump's face, this will say Donald Trump, the face recognition, whereas the behavior will be Alec Baldwin or somebody else. And now you have a mismatch between the behavior in green and the identity in orange. And then one more thing I need, which is the C sub F, which is the confidence in the face recognition. And the reason I need that is we have a very simple rule for verifying a video. We say if the two identities are the same, the facial identity and the behavioral identity, and you have confidence in the face recognition, then we say it's real. And if they're different identities, or you simply don't have confidence in the face recognition, then we say it's fake. And the reason we do this is that many of the deep fakes simply are not very good, and the face recognition fails. And so you have a low confidence, and we simply say something is wrong with this because the synthesis process just didn't work very well. Okay, so let me show you how this is going to work. We have 5 relatively large data sets that we validated against. These are the 5 data sets here, and the numbers here correspond to the number of identities and the length of the videos. And you can see we have sort of almost 2 extremes. Here in the face forensics database, we have 1,000 unique identities with only 19 seconds per identity. And here in the top left, we have only 10 identities, but 14,000 seconds per identity, and then a bunch in the middle. And we're going to validate against these data sets. This data set is of our creation, and everything else is a public database that we simply got access to. All right, now, so this is the average accuracy in the top left here of all 5 of the data sets, and these are the 5 data sets. So these are the world leaders, face forensics. I'm going to forget the names of all these, so I apologize. And what I'm showing you here is the ROC curve. So this is overall accuracy for real, that's in purple, and for fake video, that's in cyan, as a function of that threshold I just told you about, which is the confidence in the face recognition. So that's our knob that we get to rotate, okay? What I've circled here is the crossover point for each of these. So 97, 99, 93, and 98%. So in the high 90s, doing relatively well. And here, this digital forensics data deepfake challenge, the preview version of this, which came out of Facebook, you can see we're really struggling here. And in fact, you can even see that you're not even getting close to 100%. And this one really baffled us. And so when we dug into that, and I just want to mention this because I think it's important, is we actually found some real problems with the data set. So what I'm showing you here is a source face on the left. On the right is the target face. And in the middle is the result of the face swap. Now, if this was a true face swap, I would have taken this person's face, the source, and I would have mapped it onto the target. And you can see that that's simply not the case, that the face swap deepfake simply failed. And so in fact, this video, which is purportedly fake, we are saying is real, but it is, because it is this person in terms of identity, facial recognition, and it is this person in terms of behavior. So this low accuracy, we believe, is simply because some of these face swaps simply failed to actually map the identities and are simply mislabeled in the data set. And that's why we take a little bit of a hit here. Okay, Nicholas, I think I'm just about at the half-hour mark. So is that according to your schedule too?
Yeah, you're fine for time. If you want to like the slot we have is a total of an hour for the talking question. So if you have another 15 minutes.
Okay, great. I'll tell you about a few more things, then I'm happy to take some questions. So that was 2 bodies of work, one building on the other, for detecting face swap, lip sync, and puppet master deepfakes based on people's behaviors, right? Looking over relatively long periods of time of how they're moving, and we call those soft biometrics. They don't distinguish you from 7 billion people in the world, but they distinguish you from impersonators. Okay, so I showed you also earlier that the lip syncs in some ways are the hardest ones to detect, because if you think about the amount of information that's manipulated, it's relatively small. It's really just this region and then the underlying audio track. So let me just tell you some recent work that Shruti's been doing on detecting very specifically lip sync deepfakes. So what I'm showing you on this slide is a mapping between phonemes. That's what you see down here, like MBP is mother, brother, parent, FV is father, Victor. What we're going to do is we're going to look to see if the video respects the mapping between phonemes, MBP, and visemes, how your mouth has to be shaped. So you can try this. I can't see anybody except a few people here, so you can try it at home, and I won't know if you look silly. Try saying mother, brother, or parent, and try doing that without closing your mouth. So if I try to do it, this is what I look like: mother, mother. You have to close your mouth to say those specific phonemes. Okay, I see Nicholas doing it, by the way. He looks great. What we expect is that the mouth will take a certain shape for a certain phoneme. Okay, so let me give you an example of that. So on the left is going to be a real video, and on the right is going to be a lip sync deepfake. And I've slowed this down to just one phoneme, which is I'm. He's saying I am, I'm. So let's watch the real one first and slow down so you'll hear it slurred out. I'm. Okay, good, that's real. And you can see his mouth closes, yeah, right there. Now I'm gonna show you one from a lip sync deepfake where he's saying I'm so, and you're gonna hear I'm, and I'm gonna bring you into the S So you can see that the mouth is not entirely closing. So he's coming off the M and into the S, and that's, you can see that his mouth is not entirely closing, which is extremely unlikely and very hard to do and make the sound properly. So I'm not going to get into the details of how we did this because it's a whole nother talk, but we've built a very simple mechanism to extract out phonemes. In this case, we're only looking at M, B, and P where the mouth has to be closed. And then we have a simple measure of whether the mouth closes. And then we determine whether whether that's actually consistent or not. On the vertical axis here is the accuracy in classifying 3 different types of lip sync deepfakes as deepfakes, and the accuracy of classifying original videos as original. And you can see here, you know, it's not perfect. I mean, these are particularly bad ones, these T to V dash L, but you know, you're in the 80s, 90s or so. But now what we're going to do is go after all the other phonemes. We're going to go after Victor, and we're going to go after Favor, and we're going to, for every phoneme, we're going to see if the mouth forms right. And over time, as you look at more and more phoneme-viseme matching, these bars only are going to go up as you start to find some inconsistencies in the synthesis engine. Okay. And then the last thing I'll say, and then I'll take some questions, is the other thing that Shruti is working on, I'm particularly excited about because it now brings in all modalities. It's appearance, behavior, and voice. And so to motivate this, I'm going to play you 2 videos, and you can see that what I've done here is you're going to hear something in a second, and you're going to see, this is of course President Obama, you're going to see him talking, but only from the bridge of the nose up. And I'm going to play you 2 videos. One of them is real, one of them is a lip sync, and see if you can tell which is which. Okay? So let's do the first one.
Hi, everybody. On the first day of my administration, I promised to restore science to its rightful place. I told you we would unleash American innovation and technology to tackle the health challenges of our time.
Video 1.
Hi, everybody. On the first day of my administration, I promised to restore science to its rightful place. I told you we would unleash American innovation and technology to tackle the health challenges of our time.
Good. I can't take a poll of the audience, so I'm going to put Nicholas on the spot. Nicholas, which one do you think is real and which one do you think is fake?
The video is a little bit choppy.
Yeah.
But I'm going to guess the one on the left was real.
Good. I apologize if the video is choppy. That's exactly right. So if you can watch that video, by the way, I've shown this to many, many people. People instantly see that the first video is real. That there is something, like the head is moving in a way that is inconsistent with the audio. And if you think about it, that makes sense. When I go to emphasize something, and maybe I lean in or I lift up a little bit. And so, you know, our voice and our head movements are not decorrelated. But when you create a lip sync deep fake, that's exactly what you're doing, right? You're decorrelating the mouth from the rest of the head. And so what Shruti is now looking at is, if you go back to that earlier deep neural network where we brought in behavior and appearance, we'll have another pipeline into that, which is voice, and then looking for a correlation across all 3 of those. Okay, so let me just wrap up with a couple of thoughts. So first of all, this paper, the phoneme paper, and a few other papers on this topic, as well as some general forensics, are all available on my website, which is fareed.berkeley.edu. And if you look under the digital forensics tab, you'll find a number of articles available. And I think that the media has probably hyped up deep fakes quite a bit. In parts, I think it's a great word and it sounds super scary. But the way I think about this is this is not really a deep fake issue. This is a misinformation issue. And deep fakes is simply the latest incarnation into an ongoing war on information and fact and science that is disrupting society and democracy. And you know, if you've been paying attention to what's happening around the world right now, you've seen these phenomenal mis and disinformation campaigns around COVID-19 that are leading to health problems and societal problems and legal problems for everybody. And I think we got to start getting a handle on trusted information. And I think deepfakes is one component of that. Fake images and videos and audio are another component of it. Fake news stories another component of it. So it's within that larger ecosystem that I think we should be thinking about these problems. And it is very much like everything in the security world, an arms race. And one of the questions you always want to ask yourself is, well, when I build these forensic techniques, am I simply enabling the generation of the better generation of deep fakes? And the answer in this case is, well, sort of yes and no. So one of the things that I like about the way we approach this problem is This isn't a black box algorithm, right? This isn't simply building a classifier to tell real from fake. Because if that was what I did, then absolutely you can simply fold that into the generation process, particularly if you're using a GAN. So one thing is that we tend to look at things that we consider sort of more high level, more semantic. And the hope is that that's harder to incorporate directly into a synthesis engine. The other thing we do, and I will say from the outset, I don't know that this is the right decision, but it's where we've landed, is we don't necessarily make all the data and the code that we, for our forensic techniques available to the public. We make them available to forensic researchers who we know and we trust, but we don't put everything up on GitHub. And again, I'm not criticizing people who do. I think that's obviously open source is fantastic, but you know, we want to be sort of thoughtful on how we distribute these things. And I don't think obfuscation is an answer to security. And so we do publish everything, but we try to at least hold back the code and the data to at least slow down the cycle of attack and counterattack and attack. And you know, a year from now, I may have a different strategy from that. I don't know, but that's sort of where we've landed on that. So I'll just stop there and I'll stop sharing my screen and I'm happy to take some questions.
So I think we can answer the questions live. So,
oh, great.
You know, I think we can start with Rajesh, who was the first
okay. I found it very interesting that the deepfake Obama cluster is right next to the Obama cluster. Intuition behind why that cluster is not far away. Oops. Yeah, good. It's okay. I got it. Yeah, it's a really good question. The reason is that most of those deep fakes are lip sync deep fakes. And as I was saying earlier, the lip sync deep fakes are, in fact, lots of things are consistent. And so I didn't show you in that cluster, but for some of the clusters, they're actually quite far away when they are face swap deep, puppet master deep fakes, because all of the behaviors are different. Okay, have you, let me go up the top one more. So from the paper, it seems that the behavior features for the same person are different in different contexts. Does this mean that reference set has to include people's videos from all kinds of contexts? The answer is absolutely yes. So one thing we've discovered is that when, this is particularly true of President Obama, is that when he gives speeches, that context is very consistent and the way he moves and talks is very consistent. When he gives interviews where he doesn't know the questions, he's much more hesitant. He tends to look down a lot more. He pauses a lot more. So context absolutely matters. And so with politicians, you have to think about, is this a live interview? Is it a one-on-one meeting with them? Is it a public speech? Is it an interview? And we have to worry about those contexts because the way we talk can vary, and that has to be in the reference set. That's a great question, absolutely true. Let's see, I'm gonna go to the next question. The cluster figure in the beginning, what is representing the X and Y axis? Those are unit lists. We took the 190 dimensional feature vector and we just projected onto a 2-dimensional space using TSNE. So they're not necessarily meaningful axes. Of the politician data set, are all talking videos? The answer is yes. For the politicians, they were all speeches or interviews. For the face forensic data set, there's only 1 video per person, so you train and test on the same video. Yes, that's a great question. Yes, that was the one data set I didn't like because there's only 1 video per person. So we had to split each video in half. That is absolutely not ideal, by the way. So the only thing I have to say in our defense is we do well in the other data sets that have much, much more videos per person. But that's a fair question. Do you train and test cross manipulation techniques? Yes. So we're testing on lip sync, face swap, puppet master, and impersonators. Question, can you say a few words on deepfake evaluation? Unlike other machine learning problems, it's quite subjective to say if a video is deepfake or not. Yeah, so in our case, all of the videos we're using were not of our creation, but were created by Facebook, Google, DARPA, whoever, and we know the pipeline. Now, we do eventually go into the wild and we look at videos that we find on YouTube that are self-described as being deep fake. And so in that regard, I think we have a reasonably objective measure of what is and what is, a ground truth rather. Can you comment on the difference? I hope I'm not missing anything. Yeah, can you comment on the difference between deepfake images and videos? Which one is more harmful? Oh man, that's a great question. You know, I have to say for a while, I thought the deepfake images were relatively harmless. So here I'm talking about StyleGAN 2, this person does not exist. By the way, if you want to get totally freaked out, go look at this cat does not exist. It'll give you nightmares, man, the images that it synthesizes. I've started to see in the last few months more and more nefarious uses of deepfake images in form of creating fraudulent accounts on Twitter, on LinkedIn, on Facebook to push misinformation. So in that regard, you know, the fact that you can, you know, generate these things en masse and then have even more credible fake profiles is worrying to me in the misinformation space. Now, obviously, that's a little bit different than creating a video of a CEO or a president saying something they didn't, or creating non-consensual porn. So I don't know that I would say one is worse or better than the other. I just think that they're sort of different. And I've come to realize that even the fake images are a potential threat in the ability to create fraudulent profile. Sorry, let me see if I can get the rest of the questions here. Have you tried to perform deepfake detection on drone video? No, yeah, I don't know what that would look like. I don't know anything about that. And if you want to send me an email if I'm missing something here, I don't know anything about that. You're doing a lot of work on
Jonathan, if you're unmuted. Jonathan is allowed to talk from the attendees list. If you want to clarify the question.
Yeah, sure. Can I ask it? Hey, thank you very much for the great presentation. So here, of course, this is because we use drone video, as you may know, for remote operation of drones. And I was wondering if you assume, and that's why I'm like, that's kind of a crazy scenario, I think, is more, you have a compromised drone and the video feed is actually fed to the operator and it actually compromised. I want to do real-time detection that this is not a fake, that this is fake. So that's why I'm like, that's been,
yeah,
you know,
okay, gotcha. Thank you for the clarification. No, and in fact, I don't think anything we've worked on would even be helpful there, because everything we're doing is very much talking head. We've really focused on, you know, CEOs saying something, presidents, presidential candidates, and not in the sort of the general synthesis. So to that end, I'd point you to some nice work by Andrew Owens and Alyosha Efros on detecting synthesized images, whether they're people or cats or cars or presumably drone footage. And that is more going after artifacts that get introduced during the synthesis process. But what we've done, I think, has absolutely nothing. I think it would be not applicable there. From the paper, it seems that the behavioral features for the same person are different. Oh yeah, I think we've already done that. I appreciate the complexities of the signatures you're generalizing and how challenging it is to match all of them in order to bypass your signature. Of course, the question is how many features we can continue to extract and what happens when the latest scans catch up and we run out of unique characteristics. Okay, good. So one thing that I take comfort in is the fact that we are doing this over time. And so right now, as far as I know, the synthesis of deepfakes and lipsticks and puppet masters are done one frame at a time. They don't have a notion of time, and in particular time over hundreds of frames. And so that, I think, works to our advantage right now. And you're absolutely right that, you know, the more I bring into it, so now I bring in the audio track, I bring in the behavioral over time, I bring in the face recognition. Now your objective functions have to deal with all of those. And my goal here is not to stop, obviously, I'm not naive, to stop the creation of deepfakes, but it's to raise the bar really high. So if the average person can't download a GitHub repository, generate a deepfake of Elon Musk, and move the market to the tune of billions of dollars. And so I want to slow you down in terms of complexity, in terms of time, in terms of sophistication that you need to do that. You know, when will we lose that? I don't know. I think right now for this particular niche area of talking heads, we're slightly ahead of the curve, but you know, we'll see what happens in 6 months. I mean, who knows? Yeah, but it's a great question. Yeah, you're doing a lot of work on politician data sets. How far are we from making sure I won't be extorted on a fake sex tape, for example? Yeah, that's a great question. I would say the way we are thinking about it, pretty far, because we need a reference set. And a reference set for, you know, 7 billion people in the world is non-trivial. And this also gets back to the context, right? So if it's a fake video of you testifying in a court of law or giving an interview, I can have a chance. But, you know, that's not what a sex tape is, right? That's a very different, you know, those types of behavioral things that we're going after, I don't think is going to be trivial. So I think that is going to require a very different way of attacking the problem. And I don't have a good answer for that, but that is something we are very worried about. Can you say a few words about the deepfake evaluation? I think I already said that. Can you comment on the difference between deepfake images and videos? I think I've answered that. Which face descriptor you use? We use VGG. That's the 4096 descriptor. I don't think there's anything, by the way, special about it. I think you can splice in anything you want. It would be just as good. And did you consider using a triplet loss in a behavior net training? I don't know what that is, so the answer is no. And again, by the way, I think, so we use a metric loss, metric learning. I don't think there was anything special there. I think these are pretty big signals, and you saw that in the first part of the talk where, just something as simple as action units, one class support vector machines did fairly well. So I think each of the components that I described to you can relatively easily be swapped out with any of a number of different things, and you can probably eke out, either the same or slightly better performance. I wouldn't latch onto any particular thing we did and say, you must do this. I think all of them are relatively replaceable. It was nice to see that the learned behaviors did do better. I didn't show you the evaluation, but they do in fact do better than the handcrafted features, which is as you would have expected. All right, Nicholas, I think amazingly we got through all those. Thank you for whoever was.
Yeah, that was a great set of questions. Maybe I'll conclude with one more and see if we get any last couple ones. So 5 years from now, where do you think we will be? Do you think that we'll be in the world where the attackers win, or do you think that we'll be in the world where the defenders have won?
Yeah. So here I'm going to answer that with two things. One is, I think the bigger risk here is not necessarily the creation of fake content, but it's living in a world where that content can be faked. And what I mean by that is that I think today, and certainly 5 years from now, everybody's going to have the plausible deniability or the so-called liar's dividend that they can leverage. And so when that image or that video or that audio or that news story comes out, you can say it's fake. And in fact, we are living in a world where that happens. And I don't want to be partisan about it or political about it, but we have here in the United States a president who does this on a routine basis. He says that image, that video, that audio, that news story is simply not real. Don't believe it. And I think the more that the synthesis technology advances and develops, the easier and easier it is to make that argument. And I will tell you, having spent much of my time in courts of law over the last 2 decades, testifying about the authenticity of images and video introduced as evidence in a court of law, I have seen the steady uptick in people trying to cast doubt on authenticity of body cams from police, surveillance video from the FBI, video from citizens recording illegal acts, and people are like, well, how do I know it's real? And that, to me, I think is going to be the larger threat. In terms of your specific question, I think it's going to be a constant back and forth. I think the bar will keep going up, 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 and up. And I think in the end, I'm going to lose. That has to be that way. But hopefully along the way, I will have raised the bar high enough that the average person has a hard time. And that's why I think the risk of the liar's dividend is going to be that larger risk, that anybody can simply say it's not real and cast doubt instantaneously without necessarily having credibility to do that. I see a couple more questions. Do we have a few minutes, Nicholas?
Yeah, we have another 10 minutes. Let
great.
me just check the schedule, make sure that I'm not lying. Yeah, so we have until 2:30 Pacific time.
Okay. So do you think that similar methods can be applied to detect AI-generated text, tweet size, or the input dimension is too small? Okay, I love that question because this is something that we are working on with a colleague of mine, Sadia, here at UC Berkeley. So some of you probably know that there's these very, very good AI generation for generating text. So my favorite one is called Grover out of the University of Washington, where you give it a headline, like of a news story, and it will synthesize a full-blown news story for you. And you can go try it. They have a nice API and a web interface for it, and it's really good. It's sort of shockingly good. And in fact, just this morning, one of my students finished a perceptual study on Mechanical Turk, where he showed 100 participants one paragraph from a real news story and one paragraph from an AI synthesized story with the same headline. And they're basically a chance to distinguish between the two. And we were asking them specifically, can you tell if this is AI generated or not? And they just can't do it. So I don't think that the things that we were working on, which is very much, image and video based, will be applicable here. But I do think that there are techniques that can be brought to bear. And we have some early results that are very encouraging, that there are statistical artifacts in the language that is being used that I hope will be something to do with that. Because the concern there is that you can just carpet bomb the internet with fake news stories, and the signal to noise ratio will simply plummet. So I think that's going to be a really interesting space to work in. When deepfakes first came out, people were worried that it may cause a lot of misinformation during the election, but it didn't seem to happen. What do you think is the reason behind this? That's an awesome question, because I've gotten that question many times from reporters. I don't know. I have a couple of thoughts on it, though. So one is, and I think this may be the simplest one, is that good old-fashioned fake news works. You don't need to go to the trouble of creating a fake video. You can just say, Hillary Clinton is running a child porn ring out of a pizza joint in DC. You don't need a video to prove it. You just need to say it. So I think that's sort of what's happening with, we're certainly seeing misinformation around the upcoming election, and we've been seeing it for the last 3 years. It's just saying stuff that isn't true seems to work. Now, maybe we get to a point where that passes and then people need the image and the video to get there. But I think basically you just don't need it. That's the answer number one. And answer number two is, despite claims to the contrary in the press, it's not that easy to make them. You can download GitHub repositories and you can get it to run and it'll look okay, but to really get it good is actually requires a little bit of work still. Now, obviously that's going to get better. So I think the threat is still ahead of us in terms of the mass production. But I think the reality is that just tweeting out nonsense seems to get people all fired up. So why bother to go into the trouble of creating a video? Do you think non-deepfake factors might also impact users' judgment? If the video is low resolution or the facial region is small, is it harder for humans to tell if it's fake? So the answer to that second part is absolutely. Generally speaking, what I've seen over the last 2 decades is the best way to conceal traces of manipulation is downsize the image or video, transcode it at a lower compression rate, let the brain fill in, remove all the artifacts and all the glitches. And those are really compelling. There's a reason, by the way, why all UFO images, all abominable snowman, all these sort of fictional things, that why they're all low resolution and grainy and cruddy is because that sort of conceals the evidence of manipulation. I do think that actually is, you let the brain essentially fill in everything that's not there. And I do think that those are very compelling. So when I do cases in courts of law, for example, I often advise prosecutors and defense attorneys, if these are not high resolution images and videos, you should not be using them as evidence, period. When the stakes are that high, you need to have high quality imagery, particularly in this day and age where my iPhone is 12 megapixels. There's no excuse anymore for a 100 by 100 image. I like this question from Ben. Perhaps authenticated devices with cryptographic secure paths of data provenance will play a role in the liar's dividend. Great question. Let me preface this answer by saying I'm a paid advisor to a small startup that works in this space. So I have a financial conflict of interest from everything I'm about to say. So take whatever I say now with a grain of salt. There are very nice, what are called control capture systems, where instead of using the native app, you use a custom app, and it's now starting to move into hardware as well, where at the point of capture of an image, a video, or an audio, you reach in, you grab the metadata, GPS, date and time, all the image pixels, everything, cryptographically sign it, put it on a blockchain, do whatever you want to it in a way that's secure. And then provenance is proved by referring back to that signature. And in some ways, what you've done here is you've flipped the story. So the story I've been telling you is you sit back at your computer and you wait for content to come, and then you try to verify it. The other way to do it is, why should I, the receiver, verify? You, the producer, should verify. And so I like these control capture systems because they change the burden from me, the receiver, to you, the capturer. And that stuff basically works, and it works really well. And yeah, you got to work out a couple of kinks for how you break those systems, and if you hack the system, and what are so-called rebroadcast attacks, and there's a few things you got to deal with. But my hope is that we will get so fed up with the misinformation nonsense that is the internet, is that we will want to sort of start valuing trust, and that these will become part of the solution. And I think the last question is, I think, is the same one as well. Yeah. So by the way, I got this question from one of the campaigns a couple months ago during the heating of very much in the campaign, and they were very worried about people posting fake videos. And they asked me, what do you do about it? And I said, absolutely every time your candidate opens their mouth in public, you record them, and you record them with one of these control capture. So anytime a video or an image comes out, where it tried to either maliciously manipulate, edit, or modify the content, you will have a trusted recording of that you can put forward. And I think that's a really good way of thinking about this. Yeah, I mean, okay, so last question here is, even though we can get better at detecting fakes, when will we reestablish our trust in visual media? I like that you asked when as opposed to if. I don't know if the question is when or if, honestly. I think we are getting to a point where, I think it's fair to say people have a healthy level of distrust of images thanks to Photoshop, right? I mean, I think most people know that images can be Photoshopped. And I think we're entering this world now where videos are becoming less and less trusted. I don't know if we will ever get it back. It might be over. I think the only hope for that is what we were just talking about, which is the control capture, right? That we create, serious security people, like the people on this webinar and at this conference, really think about not the kind of stuff that I think of with 90% accuracy and 95% accuracy. That's all fine and good for the kind of stuff that I work on with politicians and courts of law, and you've got time and you can do this analysis. But to really work at scale, we need really good, secure solutions. I believe those things can come about, and I think without those, we're in a lot of trouble in terms of trust.
Can I ask the last question? Do you think, like you said something that, if you record everything you say and you somehow can sign it in the blockchain or everywhere, do you see a service where, let's say, Google or Facebook will keep a database and there will be,
Good.
trying to match?
Good. So this is absolutely the right question, because it's one thing to say, let's say we can deploy this control capture to the tune of 7 billion devices out in the world. Let's say people actually want to use it. But then what has to happen is that the Twitters and the Facebooks and the Googles of the world have to say, you know what? We value trusted information over untrusted information. So when you start to amplify videos on YouTube and amplify and promote tweets and Facebook posts, trust should be one of those factors, not just engagement and not just the more salacious and outrageous and conspiratorial. And so that means that the companies then have to start valuing those and tapping into that. And then, of course, if that happens, well, then we'll be incentivized to create trusted information because we want our things to get surfaced. So there's a little bit of a chicken and egg problem there, right? We have to be able to create trusted information. Google has to be able to push that up, and then that self-reinforces. But you're absolutely right that has to be part of the equation.
Wasn't that exactly what happened with the piracy when basically YouTube has access to all recorded material and they can fingerprint it?
Look, I mean, up until that, what you heard from YouTube is there's nothing we can do about copyright infringement. And then as soon as the DMCA was passed, and I'm not saying that it was a good or a bad law, is they just started fingerprinting everything, right? And it worked, and it actually works really well, right? And we could do the same thing in this space. That mechanism exists. It's just a question of, does it rub up against the profit margin of the Googles and the Twitters and the Facebooks of the world, yeah? Last question, we have 1 minute. Do you think detection using metadata is more promising than content? I think the problem with metadata is that it's very easy to manipulate it. So I can take an image, in fact, you can do this with any number of software, and simply modify the metadata in terms of GPS, date, time, everything, and you can shove it back in there. It's almost untraceable. So I think metadata is good for the sort of the knuckleheads who don't know there's metadata, and you should always look at the metadata, but I think in and of itself, it's not enough. You really do need to go and look at the content.
Okay, great. Well, it looks like we just finished on time. So thank you very much, Henny.
Thanks,
I guess that you have a huge amount of engagement. It seems people really enjoyed your talk.
I appreciate it. Thanks, everybody. I hope everybody's well and safe.
Thank you. So we're going to now move on to the next session, which is going to be chaired by Florian, which is called Weaponizing Deep Learning. So Florian.
Hi. Yeah, happy to be here and to hear about 2 talks on weaponizing deep reinforcement learning. And the first talk we'll hear about is on the robustness of cooperative multi-agent reinforcement learning. And the talk will be given by Jae-Yu Lin from the University of Toronto, which I hope is here. Is it going to be a live talk or is this one pre-recorded, Nicholas?
Yes, I'm here.
Oh, you're here. Cool. Perfect.
Live talk.
Okay.
Then go ahead.
Okay, cool. Thanks for the introduction. Hi, everyone. My name is Ji Lin. I'm a PhD student from University of Toronto. Can you guys see my screen? Okay, cool. So today I'll be
Yes,
talking
we can.
about, okay. Today I'll be talking about our work on the robustness of cooperative multi-agent reinforcement learning. This work is in collaboration with Christina Japarowska, Sai-Chen Zhang, Alberto Leon Garcia, and Nicholas Pepina. As many of you may know, reinforcement learning has gained a lot of breakthrough in the last couple of years, things ranging from AlphaGo to playing games for Starcraft. More specifically, the cooperative multi-agent reinforcement learning algorithm allows you to train a number of agents to work together to achieve a certain goal. And it's gaining a lot of attention and driving progress in a wide range of applications, from things like traffic light control, autonomous driving, and cellular-based station control. So as this algorithm and techniques are getting more and more mature, we want to be able to understand the robustness and analyze them so that they can be ready for a production environment. So just to give you a brief overview about single agent and multi-agent reinforcement learning, many of you may already know this already. In a single agent, you have one agent and an environment. The agent takes in some observation from the environment and then takes some action based on some internal policy. And once the agent action is taken, there's a reward provided to the agent. And we often formulate that as the Markov decision process, or MDP. For multi-agent reinforcement learning, instead of a single agent, you have multiple agents. So each agent takes in their own observation. These agents can live in partial observative worlds, so that the observation may be different from different agents. So once they have some observation, they make some action decision on their own, and then the joint action is sent back to the environment and the reward is provided. So we often formulate that as a decentralized partial observative Markov decision process. And the question we are asking in this paper is, since you have multiple agents working together, is it still robust, or is the system still good if one of these agents fails or gets attacked? So we'll try to look into this area. So the existing work for characterizing the surface of multi-agent reinforcement learning is very limited. One existing attack focuses more on the competitive side of multi-agent reinforcement learning. And that paper consider a case of two agents, one agent that it controls. One agent, it controls the action of a single agent and try to reduce the opponent's reward by doing some behavior in the environment. And we believe that this might be a strong assumption for a cooperative environment, because if a number of agents are working together to achieve a certain goal together, it might be hard for the adversary to come in and actually control the action of a certain agent. So the question we're asking is it possible to minimize the reward of a team by only presenting some adversarial example or modifying the observation of a single agent? So what's the impact of an adversarial example provided by a single agent in a team of, let's say, 5? So to launch such an attack, the first thing we would like to look into is how are this team of agents get trained to work together to achieve a certain goal? So existing state-of-the-art method for training cooperative multi-agent reinforcement learning uses a technique called centralized training and decentralized execution. So the idea of that is basically the agent can freely exchange their local information during training. And once they are trained, they can act independently during execution, and they don't require any communication or working to each other. So QMIC is one of the well-known model that does that. So here's a high-level architecture of QMIX. QMIX is a multi-agent version of DQN. So each agent has used a neural net to represent action value function, which is the red box you can see here. So it takes in the observation and produces a Q value for each of its action. The Q value represents the expected reward you can get if you take that action. And then the action with the max Q value will be selected as the action that the agent would take. And in QMax, in order to help train this bunch of agents to work together, it introduces this mixing network, which is the green box, to try to represent a joint action value function. So estimate the total team reward if given some action taken by the agents. And once you train this network, and once the training is done, and this green box can be removed, and agent can act on their own independently. So we're trying to attack this model. So the goal of the paper is to modify an observation to minimize the team reward. So for people who are familiar with the adversarial example, you might think you can directly just take the gradient from the Q total with respect to the partial observative of a certain agent, and then you can craft an adversarial example to do that. However, when we were trying to do this, we encountered a number of challenges. The first challenge is that the mixing network it has an assumption that all the agent who is acting in the environment try to do their best. So if one of the agent is not is taking some suboptimal actions, and the estimation by the mixing network is not accurate. And furthermore, even worse, this mixing network is sometimes not known, or it's not used in the execution environment. So it's not known to the adversary. So it becomes a non-differentiable environment to the adversary to estimate the total reward of the team. So we'll discuss how we handle this challenge. But there are also two other challenges that we encounter. One is that by applying existing attack method, sometimes we can get high misclassification, but that doesn't mean it will reduce the reward effectively. The last challenge is that in many cooperative multi-agent reinforcement learning setting, the input feature is not an image, and often it's like a low-dimensional input feature. So when you are using less input feature space, it makes it harder for the attacker to select which feature to achieve their goal, basically. So to overcome the first challenge, we first try to take this model and dissect the model into two parts. So the top part contains the things that are non-differentiable or inaccurate. So we try to use reinforcement learning to mask out the difficult part so that it can select an action or target that can present to the bottom part. And in the bottom part, we have regular deep neural networks. So you could use targeted gradient-based adversarial example crafting methods, and to create some observation that will lure the agent to select the action provided by the action on the top. So these two parts together composes our two-step methods. So this is a higher level diagram of our attack method, basically the two-step method I mentioned. So the top step one selects an action using an adversarial policy, and then the second step craft an adversarial example. So the threat model for this attack overall can be considered in two parts. In the step one, the threat model is a black box because we only need to have access to querying the agent's policy. In the second step is the white box attack, since we assume we have access to the victim agent's model. Although this can be converted to a black box with some existing methods. So next I'll go into each of those parts regarding how we implement and design them. For the first part, we're trying to learn an adversarial policy that selects an action that would minimize the team reward. And we had created two variants for this attack, this step. The first step is called optimize worst. So the goal is to select an action for agent one, in this case, the victim agent, to minimize the team reward. So from the perspective of agent one, all the other agents have a fixed policy since we're not attacking them and they're all trained. So we could agent one can consider all the other agent and the environment as a bigger environment. So we reduce that into a training and single agent reinforcement learning. The training and adversarial policy, a single agent version. So more specifically, we're turning and maximization of a discounted reward for multi-agent into a minimization of a discounted team reward that we modify, that only optimizes the parameter of the adversarial policy. Although this method works and it's able to achieve some good results, it sometimes is hard for, we find it sometimes hard for the second step to get to the action that's selected by this OW method, because we're in a low dimensional feature space. So the options for the adversarial example crafting is less. So to improve that, we extended method into a new method called OWR. OW is regularization. And basically we added a regularizer to the regular DQN training. The goal here is basically to reduce the Q value between the selected action and the adversarial action. So the intuition there is basically if you have, if the selected action and the adversarial action's Q value are closer together, then it will make it easier for the adversarial example generator to perturb the observation so that the adversarial one overtakes the original one. So that's the first step of the attack. And next I'll talk about the second step of our attack, which is generating adversarial example. So in our paper, we show that many existing method doesn't work very well. For example, variance of FGSM is not very effective in reducing the reward of the whole team. And when we try to apply JSMA, which is by default already a targeted attack method, we found another challenge related to low input feature space, as well as a characteristic of reinforcement learning. So just to remind you, the way how JSMA works is it uses the gradient information of each of its output, or in which of the action in our case, with respect to the input feature, and it tries to select an input feature that would try to promote the targeted action that you wanted to select and reduce the value of the other actions. So here the heat map shows the gradient value of this saliency map, which is called in JSMA. You can see the goal, we're trying to select one feature that would improve the value of the certain action, the x-axis, and reduce the value of other action. However, if you look at this graph, all the rows here are almost in the same color. So they are all either positive or negative. So that means if you're trying to perturb a single feature, all the action value will all go up or all go down. So it's very hard to rule the model to actually switch their action. And this is understandable in the RL setting because, for example, if you look at the darkest red row here means the health of an agent. If you reduce the health of a certain agent, you know that the chance of winning is lower. So no matter what action you select. So it's an understandable feature in reinforcement learning. So to tackle this problem, we propose a new method called dynamic JSMA. And we have two additions to the original JSMA. The first addition is we try to perturb two features at the same time. So and here is a formulation of the saliency map that is used by our DJSMA. Basically, the idea is you look at two features at the same time. And when you can look at two features, you could explore your output contour in a better way. So it help you craft an adversarial example more effectively. And the second thing is that many existing adversarial attack method uses a fixed size data, but that's sometimes not very efficient. And we decided to use a way to dynamically select this data so that the adversarial example is crafted to be more efficient. So that's the attack. And then we evaluate our attack on the Starcraft multi-agent challenge. The goal of this game is try to control the action of a group of agents and then try to defeat a team of enemy. So if you look at the figure on the right, the agent on the left are the agent that we control, and the agents on the right are the agent that are controlled by the computer. So the map we're using for our experiment is a map called 2S3Z, which contains the 2 Stalker and 3 Zealers. So a total number of 5 agents that we're controlling. So the adversary is able to perturb the observation of one of the Stalker, so one of the bigger guy on the bottom here. So to evaluate the result of our methods, we want to first understand how well does the adversarial policy works, and if we directly control the action of a certain agent. And then we want to see how well does it work if we only perturb the observation of that agent. So this is the result of our method if you directly control a certain agent. We compare our method to some baseline, for example, random action and local wars from the original agent policy, some QMix wars, which is taking the worst action outputted by the QMix model. You can see that we are able to achieve the lowest reward by only attacking a single agent. And then also we can bring the win rate from 98.9% all the way down to 0%. So that, if you look at the result for OWR, it's 9.35, which means a 10.65 reward reduction. So what does that really mean, and how do we compare to that when we perturb the observation? We'll look at the next chart. So here we shows the result that we only perturb the observation of the agent. And you can see that DJSMA plus OWR is able to achieve a 10.62 reward reduction, which is very close to the 10.65 reward reduction if you control the action. So that means we are able to reduce a team reward by only modifying the observation of a single agent in a team of 5. And then the average norm perturbation required in this case is only 8.33 L1 norm. And the figure on the right shows the distribution of the norm we need to actually launch such an attack. And OWR method is able to achieve the highest density in the lower range of the norm. So what does that all mean in terms of the behavior of the agent? I'll quickly show a demo of our attack, and then so we are trying to control a number of agents on the left side. The red agent are the ones that we're controlling. This is the normal case where the agents are just acting normally. So you can see that they're able to win the game easily. And let me quickly forward to some more important area. Oh, sorry. Yeah, in a local wars method, which if you select the worst action using the original agent network, you can see the agent that we're controlling is just runs away and it doesn't come back. The team doesn't get defeated, so it's not the worst case for the team that we're controlling. But for a case where we use our optimized worst adversarial policy, you can see the agent that is attacked try to run away. And as the game approaches the end where we have a disadvantage, this agent comes back to the game and gets attacked and killed. So also you could also see behavior of this agent effect on other agents. For example, in this case, the top left agent that we in our team is actually misbehaving because of the activity or the action provided by the agent that's attacked. So this is a result of us basically only perturbing the observation. You could see that the victim agent have some action that are not quite optimal, but eventually is able to achieve the optimum worst reward we targeted to. Okay, So hopefully I have persuaded you that robustness is an important issue for cooperative multi-agent reinforcement learning. It's important to look at both the team of agent and the environment when designing such a robust cooperative multi-agent reinforcement learning algorithm. And we propose there are, we think there are multiple ways of doing defense for this kind of attack. I think one of the way is to use a estimation of an action value or reward function of other agents, so you could understand and find them out if they are adversary. For the other detail, you can refer to the paper for informations. And that's all for my talk. Thank you.
Great, thanks a lot. So we have a few minutes for some questions while we set up the next talk. So please either chime in with questions or post them in the Q&A. Can you see the questions in the Q&A, Gio, or should I?
Yes, sure. I'll take a look and open it out. Okay, so the first question is, can you please clarify the heat map in attack step 2 slides? And are you suggesting that all feature effect action chosen equally? Okay, let me share my screen again and go back to that slide. So are you suggesting all the feature effect action chosen equally? So all the feature will, so if you look at the y-axis, each feature will have different, I guess each feature has different contribution to how you make the decision for a certain action that you select. But basically, oftentimes the change of that feature will lead to either better reward or worse reward. So basically, if you have a better health, you will have a higher chance of winning. Then your model will estimate that you will get a higher reward. Whereas, so it's often not very. You often don't find features that are I guess both ways. The second question is. Could you tell me more about how to choose the victim agent? In our work currently, the victim agent is predefined to the adversaries. Because, the reason for for making that decision is that adversary oftentimes can maybe have access to a single agent, which is probably not their choice. But I think there is from our experiment there's can be a big difference depend on what agent you're controlling. I guess it depends on the importance of that agents in this whole team. And I think when you're training a number of agents to do a cooperative work together, sometimes some agents have a higher weight, which is not intended during training, but other people will try to look at it more. So if you attack those more important agents, the effect to the whole team will be higher in that case. The next question is.
Let's maybe take one more question.
Sure. So I'll just take the question in order. Do you perform any other evaluation beside the example we showed? So in this paper that we submitted, we only evaluate for this one map. We've done actually other works that evaluate in a range of different attack, including VDN and other model, as well as different maps. So that I guess we're running out of time.
Yeah, well, thanks a lot. And I mean, of course, people can continue asking questions in the Slack channel under this specific talk. And the Q&A, I think, will stay up, so you can definitely take a look at those questions and yeah, reach out to people directly.
Sure. I'll be in the Slack chat as well if you have any questions.
Perfect.
Thank you.
Thanks. So then the second talk in this session will be given by Christopher Serrano and Michael Warren from HRL Laboratories. And the talk is on RTA3, a real-time adversarial attack on recurrent neural nets.
Okay, thanks. I'm Michael Warren, and I'm going to start sharing my slides here in a second. So hopefully this works. Oh, no.
I also have the video on my computer if you want me to play it from mine.
I need to add security permissions to share my screen here. So
okay, yeah, let me. I have the video set up and ready. So
that's easier. Thanks.
Okay, 1 second. Let me. Is the screen showing?
Yes, it is.
Okay, 1 second. There's a way to optimize for video, and I have to pass through audio, I think.
Are you playing it?
Okay, if I'm going to start playing and let me know that hopefully this works. Audio is going through or not?
No, that's not going through. When you share it, like on the bottom, there's gonna be 2 boxes you have to tick. Share computer sound and optimize for clip. I can do it.
Yeah, I see one of them, but not the other. I clicked optimize. I don't have 2 boxes on my.
I'll do that. Share computer sound and optimize screen share. But
Here, actually, 1 second. I have a.
I can alternatively exit and rejoin after I've changed the permissions to let myself share, but
I can do it. I just put it on. Okay, here it is. Share sound. You see my screen now?
Yes.
Hi, I'm Michael Warren.
And I hear sound good.
I'm going to tell you a bit about our paper, RTA3, which is joint work with Chris Serrano and Papsilla from HRL Labs and Sean Gao from UCSD. And I'd like to first hope that all of you are safe and staying well, and second, to thank the organizers for making this possible in spite of the unusual circumstances in which we find ourselves. In terms of the overall structure of the talk, we're going to start by explaining the goals of the research that we're talking about, and then we'll shift to the approach and the particular experiments. The main goal of our work that we're presenting here was to try to carry out real-time attacks on RNNs, so attacks that could actually be performed by an attacker who's on the wire with the system in real time. And the observations that I think were key to our development were, first, that RNNs have some kind of state or memory. They have to in order to be able to handle data that's coming in through time or in some kind of sequence. And therefore, if you can iteratively attack the RNN at specific times with specific magnitudes of attacks, you may be able to actually corrupt that memory in a way that progressively causes the RNN to misbehave. And you may be able to do this in a way that doesn't actually require continuous attack, so you can actually schedule your attack. And when we started thinking about that this is really kind of a scheduling problem, we started to think that deep reinforcement learning might be a good way to carry out the attack because it's quite good at doing these scheduling style tasks. So in addition to just the real-time aspect and the RNN aspect, the other goal that we had in mind was black box. So we didn't want to rely on white box access to the model. Let me briefly describe some of the related research, and a lot of what I focus on here is in the audio domain, and that's largely because, as you'll see below, the experiments that we've carried out for the most part have also been in the audio domain. Now, of course, the first paper there, and I'm not going to speak through every piece of this chart, but the first paper there is obviously one of the milestones for looking at attacks on RNNs, the paper of Paperno, McDaniel, Swamy, and Harang from 2016. There's then very important work from Carlini and Wagner in the audio domain. That's Whitebox attacking Baidu's deep speech, the Mozilla implementation, and that's a model that we're going to also describe attacks on in a bit. That's a Whitebox attack. There's recent work from last year of Tauri, Kamseti, Chu, and Vimuri that also attacks deep speech. That's an evolutionary approach, and it's looking at two-word target phrases. It is black box. That one isn't really suitable for real-time attack, but there is some more recent work that is, such as the work of Gong Li, Polabauer, and Shi. And that work in particular uses an imitation learning based approach to train a attack policy that can then be used in real time. That's working with the speech command data set and the speech command CNN model, and it's looking at 1 second audio samples. So quite small audio samples. Some of the stuff that we'll show in a bit works with considerably larger audio samples. There's a recent interesting paper of Vijay Aragava and Roy, and that paper does something somewhat similar to the preceding paper, which is it pre-trains a hybrid encoder-decoder model that's used to generate attacks using teacher forcing, and then follows up using a bit of reinforcement learning to refine the model. And that makes this particular paper a bit closer to our approach, which focuses on RL. And finally, the paper of Chang, Huang, Yu, Jin, and Wang. This paper was, I think, quite inspirational to us in terms of some of the techniques that they use, as we'll describe. It's a real-time capable attack, and it's also on the speech commands use case. The one principal difference, I would say, in terms of the kind of high-level categorization of this paper versus the results we're presenting here is that this was a white box attack, and so there are some differences with what we'll present. That was by no means a thorough overview of the literature, and there are plenty of other relevant papers. Those are just some of the highlights, I think, related to our research. As I mentioned, we're using reinforcement learning. This is reinforcement learning in one slide, which is obviously not enough to actually get across the idea, but in case you haven't been doing a lot of reinforcement learning lately, let me just remind you that the overall setting is you have an agent that's interacting with an environment. The agent consumes state reward pairs, and it produces actions, and it's trying to maximize its discounted reward as the optimization task that we're trying to solve. I'm now going to tell you about the details of the approach. So the parameters here are the target model, which is the network being attacked, the attack function kappa, which consumes the action or the signal produced by the attack policy and then carries out some kind of transformation potentially. So it could be some kind of generative model where the policy is actually learning a parameter in the latent space of the model, but in many cases it will just be the identity function. Just keep in mind that you may want the policy to generate a signal that doesn't directly feed into the network, and that's the purpose of the attack function. There's a pre-processing function possible as well for similar reasons. And then there's the reward, and that's a parameter of the algorithm that allows you to potentially emphasize different features of the attack that you'd like to highlight, like the naturalness of the signal being generated. In terms of assumptions, a very important one here is that this is a controlled attack in the sense that we assume the attacker is capable of directly manipulating the input to the RNN. It is quite interesting to look at uncontrolled attacks, and that's something that we're doing at the moment. But here we're talking about this controlled case where the attacker directly manipulates the input to the network being attacked. And there are a few other generalities there. So we often use PPO as the RL training algorithm. I'd now like to hand things over to my co-author, Chris Serrano, who's going to tell you about the experiments.
Our initial work attacked a system that many here should be familiar with, the Deep Speech Automatic Speech Recognition System. And this was originally work from Baidu by Hanun et al. And we targeted the open source Mozilla implementation. The attack model in this case was to perturb a waveform such that a keyword does not appear in the transcription of a phrase. So the phrases should be sufficiently large. They were 10 words on average. And the attack should be effective against phrases and speakers not encountered during training. So the desire here is to train a policy that will generalize. Further, the attack should be carried out in real time. And in this case, it's untargeted in the sense that we don't care what that keyword is pushed to. We just wish for it to not be transcribed correctly. For this task, the audio was presented in the email frequency spectrogram in 40th of a second time slices. The audio was 16 kilohertz mono, and thus the agent at each time step sees an 84 by 84 slice. The architecture of the agent feature extraction layers was a model popular in the RL literature, not really specific to the task. And the output from this feature extractor is flattened and then fed to an LSTM, followed by densely connected layers. Finally, we output a mu and a sigma that parameterize normal distribution, and the action, that is to say the perturbation, is sampled from this normal and applied uniformly over the waveform of the current time slice that the agent is looking at. We reward the agent for removing the keyword while simultaneously maximizing the blue score. Additional similarity measures can be folded in here. The mean squared error or the cross correlation could also work. They just need to be normalized into the same range, since the agent will see a single scalar reward. The environment we trained in utilized a training set of phrases from the LibreSpeech dataset, and all of these phrases contain a targeted keyword. And at the start of each episode, a audio sample is selected at random from the training set, and where we start in that audio sample is also selected at random. So the agent doesn't see a fixed set of audio samples. And this also allows for the possibility that the keyword will not be present in the audio if it happens to start at some point in time after the keyword has passed. On the top here, we have the initial results from an iterative attack on a single audio sample. So here we weren't working with a training set, we just had a single sample. And the plot on the right, the blue shows the perturbation that's applied, and the red is the original waveform. And this does something kind of interesting. We're training on a single example, so it starts perturbing before the keyword. So that the first blip is the keyword, and here the word is go that we're targeting. So here we'll play the original audio.
Go. Do you hear? Go. Do you hear?
And that's the large attack, and you can kind of hear that it's front-loading that attack.
Go. Do you hear?
A slightly smaller attack.
Go. Do you hear?
And here we're applying noise, basically from normal as defined by the agent. And on this second set, we're attacking a longer phrase. Here's the original audio.
There is no occupation that fails a man more completely than that of a secret agent of police.
And here we're targeting the word secret. Deep Speech struggles with this particular sample, but we're interested in removing that word secret.
There is no occupation that fails a man more completely than that of a secret agent of police. There is no occupation that fails a man more completely than that of a secret agent of police.
And that's with a smaller attack. The next iteration of our attack was performed on VGG Vox, utilizing the Vox Celeb dataset. And the Vox Celeb dataset is a celebrity voice dataset that was culled from YouTube by Negrani et al. And helpfully made public. And along with the dataset, they developed a speaker identification and speaker verification model. So in the identification case, we want to classify an audio sample as a particular speaker. And in the verification case, we want to verify that two samples are the same speaker. So VGGVox utilizes, as its name would suggest, the VGGM convolutional neural net architecture. And it outputs a vector in a learned Euclidean space. So in this case, the similarity between two samples corresponds to some distance metric over this space. So in the verification case, if two samples are some small epsilon distance from one another, then we consider them to be the same speaker. And in the identification case, given the output of some set of candidate speakers that we care to classify, we can then present new samples to the model and classify this new sample based on its distance to our candidate set of speakers, shortest distance being our classification, and maybe we can also set some threshold on how close it needs to be. And so we wanted to extend our work to a targeted case. So we selected the speaker identification task. And in this case, we want to push a specific speaker A to some other specific speaker B. And again, we wish for this attack to generalize to samples that were not present in the training set, and ideally for it to be performed in real time. So given this is an RL framework, the training will be iterative, but we wish for this attack to be successful as soon as possible. So ideally, the number of iterations necessary to perform a successful attack falls over time to just a handful of forward passes of the network. And that could be realistically performed in a very small amount of time with very little real-time delay. Our initial approach against deep speech had a few key shortcomings. In particular, we were perturbing the waveform directly in the time domain. And the rather simple attack function of a uniform perturbation over the slice of audio we were presented required hand tuning, as it was dependent on the ambient volume of the audio. Additionally, our agent's feature extraction architecture was borrowed from the RL literature and not specific to the audio task. So the very interesting work of Chang et al., audio adversarial example generation with recurrent neural nets, utilized the short-time Fourier transform as a state representation. And this allowed them to perturb in the time frequency domain and then invert back to the time domain to recover the audio. And if you're dreaming up actions for an adversarial RL agent, then this time frequency representation is a much more interesting space to attack. And it removes the need to hand tune the size of the perturbation in the time domain. Additionally, we tailored the architecture of our feature extraction to the structure of the state representation. So our convolutional filters operate specifically in frequency and in time. And providing the polar representation of the state space directly to the agent also offloads it from requiring to learn these features, angle and magnitude. In this case, our attack function is what we call a phase shift attack. The agent outputs a rotation to be applied frequency-wise, so we're not altering the magnitude of any frequency, just its phase. And this idea was inspired by Papsilla, a member of our team, who recalled that humans are not particularly good at hearing phase shifts, and this attack might be more difficult to detect. In practice, iteratively applying this attack does lead to audible distortion, but it proved to be less destructive than directly perturbing the STFT coefficients. And here we reward our agent for reducing the distance to the target class while maximizing the distance from its true class. We additionally reward it for doing this quickly in terms of number of iterations. And so here we have some initial results. In the first case, we were perturbing the coefficients directly, and we had 3 candidate classes, and we were trying to push a sample from class 3 to class 1. So here we'll play some audio.
Catherine's disposition was not naturally sedentary, nor had her habits been ever very industrious, but whatever might hitherto have been her defects of that sort,
in 1665, written by a citizen who continued all the while in London, never made public before.
And that was class 2. The first one was class 1. This is class 3, and this is the one we wish to push to class 1.
Some of the Scottish immigrants, heated with Republican enthusiasm, and utterly destitute of the skill necessary to the conduct of great affairs, employed all their industry and ingenuity.
And here is the unperturbed test time sample of class 3.
But he was placed under the control of a committee.
And that's correctly classified. And here we wish to push that speaker to the female speaker class 1.
But he was placed under the control of a committee.
And we do successfully do that, although the distances are pushed further out in general. We would like this class 1 number to be much smaller, but it does serve to prove the point. We would also like the perturbation to be less destructive than it currently is, or at least than it was with this first example. So with the second example, we have the phase shift attack, and here we're specifically moving Adam Driver to Alan Alda. So here is the unperturbed sample.
Idea that I had going into it, but it's still kind of excited by the process.
And here is the target class.
Put down by the medical profession.
And the perturbed sample.
Idea that I had going into it, but it's still kind of excited by the process.
And so we find the phase shift attack to be much less destructive, although still maybe more than we would like. This training didn't specifically have any reward for similarity to the initial class, but that is something that could be added in. Again, this can be performed in real time, a very few number of iterations, 2 or 3 on average. And the output is kind of intuitive to read. Our target class has this kind of cutout between 6 and 8K, and we see that as well on the perturbed audio.
And this is our team who carried out the work presented here, and now we'll turn to questions.
Perfect, great, thanks. So we have a few minutes left in this session, so I think we can take maybe one question right now, and then after that we have a big break plan. So there's also a Slack channel dedicated to this paper where people can ask further questions. So we have one question in the chat. If either Christopher or Michael.
Yeah, sure. I can take that.
Cool.
So how long would it take to generate an adversarial example? 2 to 3 iterations, right? So each iteration is just a forward pass of the network, right? So if you're on a GPU, I guess it depends on how fast your system is, but very quickly. We've also started extending this to image and video, and we find that domain is actually much more forgiving than audio. The perturbations are much more difficult to detect. I think we end up with something that's a lot more adversarial in the standard sense, where maybe a human wouldn't even be able to perceive it. And there we can do a single forward pass and generate a successful adversarial example.
Cool, then thanks everyone for attending this session. Looks like we have a 25-minute break on the schedule now. So I don't know, Nicholas, if you wanted to say something about how things are going on from here.
Yeah, so we just have a break, and then we will be back at, depending on what time zone you are in Pacific time, it's 3:45 for the final session, and then some closing remarks at the very end.
Nicholas, do you want to retry the experiment?
Yes, I will. I will test now. I was just going to wait a few minutes just so people all left and let us test in peace.
So do you say share computer sound or optimize?
Yeah, so I noticed that you have to close the thing and open it back up in order to get that to come back. So after you've shared the application, it looks like you can't change it afterwards, or I couldn't find a way. But right, I think I can do it. So let me just try. So let me get the file. This one's I want. LipNet. Okay, let me go and test it and just let me know if it correctly works.
You can also